This event, USTE, is an amazing event. Always a good time, so everybody give a round of applause here. Everybody, so much effort. So much effort. So I'm going to be talking about some electronics today for y'all, evidently. And what I would like to start with is essentially talking about motors and how to select the right motor for your rig, especially if you want the best torque density. It may not be as straightforward as you once thought, or maybe it is. So I'm going to use this as a whiteboard. There's going to be some formulas and stuff. And let me know if I need to write any larger for you to see, or if you can't hear me in the back. So let's start out with a general question. If you're going to select a brushed motor for your rig and you want peak torque, what would you select? You got any guesses out here? What would y'all select? Just off the cuff.
No idea.
No idea.
Just torque?
Just torque. What do you want?
Probably 45, 35.
55, 65.
6 turn.
3,300.
Right, we're in the right direction. We are in the right direction. So what I'm going to do is show y'all with math why certain motors will produce more torque for your system and essentially why it happens that way. So we're going to start with a couple of formulas here, like I said. Motor constants we will start out with over on this side. So if we are essentially looking at constants, we have kV times KT, and this equals 1. This is a constant, so we will know the voltage constant, the RPM per volt, multiplied, nope, I did that wrong, times KT, times our torque constant, and if our units are in Newton millimeter or Newton meter amps and rads per second, it equals 1. If we go to ounce, inches, and amps, multiplied by kV, this is 1.355. We can scale these to anything. Today we're not going to use units of torque, we're just going to use our imaginary units of torque because it makes the formulas easy. But we could convert it into either an ounce, inch per amp, or a radian per second with the Newton meters. Where is it here? Newton meters per amp. So this is just a scaled formula here. Watts? Everybody probably knows watts.
Right here. Yeah, right
We
here.
know
Right
watts.
He's right here. Oh,
Watts, and today we're going to use for watts just amps times volts. Get this out of the way so we can see. Next one, torque. Torque, once we know our KT, amps times KT is torque. Nice and easy. Now, Ohm's law. I assume somebody probably knows Ohm's law here. Now let's remember it. With amps times ohms equals volts. Nice and easy. And then we're going to talk about heating a little bit at the end. And heating is the amps squared times resistance.
You meant volt equals amps times ohms, right?
What's that? Robert?
Ohm's
Ohm's law. Sorry, this is Ohm's law.
Oh, the Ohm's law. I
Law.
Gotcha.
There we go. There we go. All right, so those are our basic formulas. I think I got everything here. And now what we're going to do is we're going to run down first brushed motors and show you how we can select essentially the best torque for our brushed motor. And it maybe will surprise you, maybe it won't. So I'm going to do a little chart right here. We got our turns, have our kV, KT, phase resistance, phase ohms, brush ohms, total ohms. Then we work out our amps.
Hey John, you want a quick testimonial?
Sure, while I'm writing these down.
Bruce Truggy just went into the fish pond with a Trailmaster BLE waterproofed by Holmes Hobbies themselves and a Polar Pro Stubby, which comes waterproof from Holmes Hobbies. And it was sitting in there for probably close to 10 minutes, and it's driving just fine right now.
All right. Waterproof? We don't say it's waterproof. Water resistant.
It's water resistant because we like to listen to the FTC.
Right.
So yes, so here you go. Bruce Truggy survived, and it's got all Holmes electronics in it.
Excellent.
And a Holmes turbo.
You got what getting it out?
Drew got wet, and then Corey did not get wet because he used rake.
Like I said, the rake.
Well, you got one burned up this thing, this motor held up.
That's right.
All right, let's see if I can keep this chart legible for y'all. So what we're going to do is we're going to assume that a 27 turn is where we're starting from, and we're going to make all the formulas based off of that. So I know that the KV of a 27 turn motor is right about 2,000 KV. It changes a little bit with different construction, but more or less we can assume that that's about the speed, especially if we're comparing to a brushless motor. So it's 2,000 KV. As I said, for our torque constants, we're going to scale this one today. We're not going to use hard numbers. We're going to use easy numbers. So I'm going to say that the KV, or the KT, the torque constant for this one, is going to be equal to 1. Our phase ohms, so the resistance of the coils inside the motor, we're going to go easy today, and we're going to assume that the ohms are 1. The brush resistance, again, I'm going easy today. So ohms of 1. Our total ohms for our motor now, we can deduce 1 plus 1 is 2. Maybe you follow me. Now, let's go through my chart. The next thing we need to figure out is the amps of the system.
From Holmes Hobbies back in the corner. You see the huddle of people, they're all
if we look to Ohm's law, we know that amps
doesn't cost
times
anything.
ohms
It's a
equals
free
volts, and we
class.
can
Go
deduce,
learn from John
we need to
Holmes
say what
of
we're going to apply
Holmes
to it.
Hobbies.
Let's say 10 volts to make this nice. 10 volts. And I might need some help with the calculator here in a little bit, but right now I think I got it. So we have a motor with 2 ohms resistance on it. We're going to apply 10 volts to it. How many amps is going to come out the backside of the motor? How many is it going to draw?
5.
5. Excellent. There we go. So making sure I'm staying on lines here. All right. Right there. 5. Here's our. These are going to be the numbers that matter. Now we got volts. Oh, I already had volts on here somewhere else. We'll just put it down again. Now, since we're not using units of torque specifically, we can just literally multiply the torque constant up here 1 times our amps, and we get our torque output down here. So it's going to be 5 times 1. Everybody, 5? 5. And then if we want to go ahead and do our power in watts, it will be our amperage times our voltage, and that is 50. So now we've got a baseline. 50 watts of power. This is assuming 100% efficiency. Of course, it's going to be simplified for today, and 5 units of torque. Now, we're going to start back up here again. 2,000 kV for a 27-turn motor. Half speed of that is going to be 1,000 kV. And we know from experience about a 55-turn motor is 1,000 kV. Now, the torque constant, when you have your motor speed, your torque constant doubles. So now for our phase amps, we get twice the torque for the same amount of amps. However, you'll see it's not exactly straightforward. So our KT is now 2 units. And we can go back to our motor constant formula, and you see it's a linear relationship on there. And that is why the KV and the KT, the voltage constant and the torque constant are, it's easy to figure out. So we can do numbers like this. Now, the next one, our phase amp resistance. If you have your motor speed, and we start with, of course, the phase ohms of 1, what would y'all guess that the new motor resistance in the phase would be? So we're starting at 2,000 kV, we're going to half speed to 1,000 kV. What is our resistance going to do? Double? Good guess. Half? Good guess. Anybody else? I mean, that sounds reasonable. So what's going to happen is it actually goes up by 4 times. And it's a little weird that it does that, but when we look at some of the other formulas, it actually works out. So 4 ohms. The reason why this happens, we've got twice the turns, right? So you would think it's half the wire size. It's going to double in ohms, and that would be correct. But you have twice the turns, you also have twice the length of wire to make those turns. So we have half the size and double the length. Now we are 4 times higher resistance. So that's why it goes in that way. It's not linear. It is actually doubling every time you have your speed. Our brush resistance is going to stay the same. We're going to assume that the brushes are brushes. It's going to be the same brushes on all these units. We're still at 1 ohm for that. Total for our motor now is 5 ohms resistance. What is it going to draw on the amperage now? 5 ohms resistance, we're putting 10 volts to it. 2. It's only going to pull 2 amps now for a 55-turn motor. And by the way, these are actually pretty close to real-world numbers. Again, our torque units are not going to show us what the real torque is going to be, so we're not applying units to it, but it is scalable. All right, so our volts were still at 10. Our torque now, we are pulling 2 amps. Let me make sure I'm doing this right. 2 amps. Our torque constant is 2, so 2 times 2, what are we at now? 4. As you can see, when we went from a 27 turn to a 55 turn motor, our torque actually dropped from 5 units down to 4 units. But we're only pulling 40 watts to get it. Power is our volts times our amps, so we're at 40. All right, so now let's go in the other direction. We're gonna double our motor speeds. We're gonna go from 2,000 kV to 4,000 kV. About a 14 turn motor, 15 turn motor is the right speed. So we're gonna start here, 4,000 kV. KT, we doubled our motor speed, so our KT gets cut in half. This is going to be 1/2 unit. Right. Our phase ohms here. We started at 1, now we're going in the other direction. What do y'all think is gonna happen? Yeah, it's gonna be a quarter. Exactly, so 0.25. Our brush resistance did not change. Our total ohms on this motor is now 1.25 ohms. Our amps, let's see if I did calculate that. I did not calculate that yet. So can anybody help me out here? We got 10 divided by 1.25. Buddy, I think it's gonna be 8. I think. Seems about right.
Yeah, 8.
Double check? All right, 8. So 8 amps. 8 times 0.5 for our torque constant up here is 4. And we're still on 10 volts here. So 4. Look at that. We went in the other direction. We went faster and we lost torque again. But in this case, we are at, let's see, how many watts? We got 10 volts. We are at 8 amps. It took 80 amps for this motor to produce the same torque as the 55 turn on 40, or I'm sorry, 80 watts. 80 watts there. So as this lays out, you can kind of see there's a golden zone right here in the middle. This 27 turn motor is producing the most torque, and you know, it's the same efficiency as the 55 turn, but definitely more efficient than our 14 turn at producing it. And if you look, I haven't proven this with running the dyno, but what I am thinking is that when our phase amp and our our phase ohms and our brush ohms are equal, that is when we're in the golden zone for a brush motor for producing torque. So it doesn't matter really what voltage you are applying to it, this is going to give us essentially our best overall results. Now from back in the racing days, does anybody remember what was said to be the highest torque motor when you're racing? Anybody used to be a racer? It's a 27 turn. It's almost like they kind of knew. So what can we do if we want to get more torque out of this system? Now you can always use a longer motor. A bigger motor is always going to be able to produce more torque before it saturates. And instead of having a 27 turn motor, we'd have a 21 turn 550. But it's the same speed. But since the resistance of the motor would be lower, you end up getting more torque out of it. And alternatively, what if we reduced our brush resistance? If we went to say silver brushes versus copper brushes, now this formula is going to change a little bit. Everything is going to shift over, and instead of the 27 turn being in our magic zone, maybe it's a 25 turn. Well, the same thing for going to a hand wound from machine wound. As much as we can reduce the resistance of that brush and that commutator interface, we can actually bump the speed up just a little bit. Now it's not a whole lot. Most people may not notice the difference on there. Of course, going from machine wound to a hand wound is a huge difference in there. Pretty much twice the torque that you can pull out of it. But as far as, you know, having that golden zone move, I don't know if anybody could actually perceive a couple of turns here or there. That's more of, you know, esoteric stuff at this point. So let's even this up a little bit. Our 55 turn motor is going to be spinning at half the speed of our 27, so it's going to be making a lot less power on top of everything else. It's going to be kind of a poofy motor. Not everybody wants that. What if we doubled our voltage on that 55 turn motor? I haven't run the numbers, so I'm kind of interested to see what happens here. We are still a 55 turn motor. It is still 1,000 kV. Our torque constant has not changed. It is still 2 units. Our phase amps, it's all the same. Our brush, or our phase ohms, our brush ohms, all the same. They're still 5 ohms. Our amps now, we have 20 volts that we're applying to it, divided by 5 ohms. What would that be? And we can look over here and cheat. It was at 2 amps. We doubled the voltage. It's going to go to 4 amps. Double our amperage. Now our torque, we have the amp units here multiplied by our torque units. So 4 times 2. Hey, look at that. We doubled our torque. And we are at, let's see, 8 times 20. What's 8 times 20, y'all? 160. 160. Our power went up 4 times. So you doubled both your torque and you doubled your wheel speed. Looking at it, man, it's looking like this 55 turn motor running on twice the voltage is actually going to give us a lot more torque. Of course, we could do the same to the 27 turn. We run it on 20 volts, and what it's going to do the same thing. It's going to double torque. It's going to go 4 times the power. Now, I don't know if I can really get into it easily, but the next thing that we would look at this point is the heating losses. And the heating losses are always going to be what is your problem in the system when you're working against it. You're trying to get more torque out of it. It's just, heat's the bad side of electronics. And in most cases, now, we're looking at the slow motors, the heat's actually going to be the same until you start saturating your brushes or saturating the coils in the motor. It's going to work out the same, because as we go up 4 times in phase resistance on there, we actually have heating that is the square of the amperage. And so it actually balances out to where a motor is a motor is a motor. And until you get too fast and you start saturating the brushes in this case, they're all essentially going to make the same amount of torque as long as you're spinning them the same speed. So that is why the 55 turn motor on twice the voltage is essentially, well, in this case it's actually beating in torque. But again, if we doubled our voltage on the 27 turn, we'd even the playing field, and the 27 would be even more powerful. So a really long-winded way to essentially say, hey, for brush motors, we can tell that maybe the racers knew what they were talking about. That 27 turn, or something similar in speed, like a 13 turn, a 5 slot, a Crawlmaster, that's our golden zone of torque now. Now, let's say you don't even need all that wheel speed. Maybe you don't want that high of a kV. A lot of people love 1,000 kV to 1,500 kV, like 55 turn to 35 turn range. And in that case, if you don't feel that you're losing torque, if you don't need more, then that's all that you need. So really, you should select your system based on the wheel speed that you want, the voltage that you're going to run, and then of course the gear down of the system that you get. So like on a Cabra, if I'm going to install a brush motor into it, I'm not going to install a really fast brush motor into it because it just doesn't have enough gear down to support it. So if I put a 14 turn in there, man, it's going to smoke immediately. If I put a 27 turn in there, it's not going to really be that happy. But if I bring it down to a 35 turn, it's not going to pull so many amps that it's going to smoke right away. And that's kind of the downside. That's the caveat to all this, is you got to have enough gear down to deal with it. Now, I would like to get into brushless motors too, but I don't want to redo all of this. So if we're looking at a brushed motor system, we don't have our brush ohms in here. So we can get rid of all of these. And what would happen is all we have on this side, the phase side, is we have the ESC. And the ESC is going to be on the range of 1/10 of an ohm or 100th of an ohm, depending on how large the ESC is. So something like a Mamba X, the phase resistance on that one is 0.0012 generally, or 0014. And then you add in the wire links, it's not much more. But if our balance zone is when our phase resistance is the same as our brush resistance, or in a brushless motor commutator is our ESC, then it really pushes this kV up. So instead of the golden zone of torque being 2,000, it's going to be somewhere up 4,000, 5,000, 6,000. However, up here, our heating is going to get us in the ESC in that case. And so what ends up happening when you're on the trail, well, you're only giving it a little bit of throttle, but that really fast, that high kV motor still asks for a lot of amps. It asks for twice the amps. Let's say, we go from 2,000 to 4,000 kV. It's asking for twice the amps. If we go up here to our heating, it's 4 times the heat in your ESC because it's a squared factor. And that beats on ESCs really, really fast. So really the moral of this story is that you can't go too fast, even in a crawler system with a ton of gear down, because your ESC will not like it. It'll overheat long term on the trail. You get, what I consider like a soft throttle feel. You'll lose drag brake, you'll lose torque. And over the long term, if you're on the trail for a couple of hours at a time, it's just not going to be happy. It's not going to work out. And that's why we're actually seeing, I'd say the smarter companies that have been doing it for a long time, they don't offer KVs above like 3,800, 3,500, somewhere in that range. Because on the trail long term, it hurts the ESC, because that's really what's left in this equation as far as the heating on there. And that's my recommendation. If you want brushless, if you want maximum torque in brushless, we're going to be way up here in 3,500 kV. You probably don't need that much wheel speed. You probably don't need that much torque. You don't need that much power, but it is there if you need it. And in reality, most people are going to be down in 2,700 kV, 2,200 kV, or 1,800 kV, and still have all the torque they need, all the power that they need, and still have a system that works. Like I said before, you got to have enough gear down to work with the speed that you want out of the system, along with the voltage that you want out of the system, and it all kind of comes together. Of course, here there's a lot of small tires, so you gotta work with the rollout of your tires as well to get to it. This is a lot of math. This is a lot of complication. When it really boils down to it, what do we know? I'd probably like to run a 3500 kV in almost everything that I have. Maybe 2700 if I don't want too much wheel speed. That works for most rigs in the market running on 3S LiPo. I could just say that, and we could avoid all this if we just said, hey, what do you like to run? That's probably what your friend's gonna like to run. And that's really what I recommend, is like the guys in your group, wheel one of their rigs. If you like the speed that it has, get the same speed motor. If you want more wheel speed, get a little bit higher kV or run a higher voltage on there. I wouldn't ever suggest gearing up, of course, because when you gear up, you actually end up having more phase amps on the motor. You have more heating in the motor. You have more need for your ESC. You have more heating in there. And let's say you doubled your gearing on your rig, you have twice the amps, but since the heating is the square of the amps, your heating just went up 4 times in your ESC on the phase side. So you can't chase that tail, in a crawler at least, or else you will burn out components, or at least have something that is not optimized. And in this case, I'm talking about torque output on the system. So a lot of talking there, a lot of terms at you, throwing some formulas at you. Does anybody have any questions? When the rubber hits the road, maybe it's a little bit less complicated for us, right? So any questions pertaining to this right now?
I used to do trials, and actually the smaller motors, 250 versus 300, you were a smoother driver. You didn't have the sudden power, but if you knew ahead of time, most of the people were smoother. Well, I'm saying, like we were rock crawling, were smoother versus a higher output system. It might be jerky, a little bit less controllable.
Absolutely, and that's like considering a 2-pole versus a 4-pole, or a 5-slot motor like the Crawlmaster versus a 3-slot motor, which would be a Trailmaster, Torquemaster, and pretty much everything else in the market is still 3-slot. So 3-slot motors are going to be a lot more torquey, they're going to have more drag brake, and they're going to have more pop off the line. It's not going to be as controllable. The easiest way to describe the difference between them is when we're at this 2000 kV range, that a 3-slot motor is actually going to have a lower resistance in our phase by a little bit, about 20% or so. Whereas a 5-slot motor has a little bit more resistance to it, but you gain a slower startup. And that is the more tractable, that is the more controllable power. And more or less, that's how motors work. Whenever you smooth out the startup of a motor, your phase resistance ends up going up just a little bit, and so your amp efficiency goes down a little bit. It won't produce as much stall torque. And that's a constant that we can, it's not guaranteed. There are ways to make really smooth motors that are also torque dense, but when you're trying to compare apples to apples, that is the trade-off. If you have a motor that's a little bit smoother on there, it's not gonna produce as much torque, it's not gonna have that inrush of current so much, and it's gonna be a little bit easier to control. And in a crawler, it's like 3-slot, 5-slot, or going from a 2-pole motor to a 4-pole motor. Usually higher pole count is a little bit smoother, not always, but it's usually the case. It's kind of a constant somewhat lean on. So does that answer your question? Sure. Yeah, more or less. Yeah. And if we go to a much faster motor, much faster motor, they become punchier and punchier, and that gets into the inductance of the motors, because the inductance of the motors end up getting also cut in quarter along with the resistance, and it ends up being almost an uncontrollable system. So if anybody's in the the racing scene, you get a motor that's like a 3.5 or a 4.5. It gets so punchy that you can't control it, so you end up either turning down your throttle, or you add a little bit of throttle ramp time depending on the controller, so you can actually control it and still have that wheel speed on the back end that you want. So, always a fine balance. A little bit different for crawlers versus racers, but there's always that concession that has to be made. One thing about motors is you have one thing that changes, and it's going to change something else along with it. It's always a balance. Anybody else? No? We good? Y'all kind of understand now? There's going to be a golden zone for torque, essentially. It's either going to be the ESC that's hurting, or it's going to be the brushes that are hurting, but you push too fast, it's going to hurt you. Or if you go too slow, you're not producing as much torque, it's not going to be optimized. And surprise, surprise, most people like that 1800, 2000-ish kV range. And to me, it's, I guess, not a surprise, but I've been doing this a while, so. All right.
If you guys like the channel and want to help it out a little bit, you can click that join button and actually become a channel member. Members get special privileges, maybe even some member giveaways. So make sure you check that out. And as always, subscribe, like, and share. Thank you guys for watching.